So today we are starting section 7.3. It's all about power functions and function operations. We're doing this lesson over 2 days. I just kind of made it so it cuts off and then it picks right back up where we left off starting tomorrow. So if you want to just do like one title page, that's fine. Our goal for today is to perform operations with functions, including power functions. And then tomorrow we're going to look at compositions of functions. All right, this is sort of a definition for operations of functions. You can see that I put, this is on page 415. It's in a big green box. So if you don't want to write all this down, maybe in your notes just put see page 415 green box, and it has all of this there for you. It even has some examples in the box. So there's a lot more information in the box than is what's on the board. But basically what we're saying today is we're going to have two functions. We're going to have an f and a g. Sometimes they might not be called f and g, but you'll have two functions. We're going to create a new function, usually called h, and that can be defined by performing any of the four basic operations on f and g. So either we'll add f and g, we'll subtract f and g, we'll multiply f and g, or we'll divide f and g. Those are the four basic operations. Sometimes a little bit of a tricky part is to find the domain. Remember, the domain is another way to say the inputs or the x values. So the domain of h, the function that we're creating by doing these operations, just consists of the x values that are in the domain of both f and g. So if there's some sort of restriction on the domain for either f or g, that restriction will hold true when you put the operations together, or put the functions together using an operation. In addition, you guys know that you can never have 0 on the bottom of a quotient, or a fraction, if you want to think of it that way. So if you are having something like f of x divided by g of x, just be aware that any value that would make the g function a 0 cannot be in our domain. So, for example, if you had an x on the bottom, you would say that you cannot put a 0 in. So x cannot equal 0. Or if you had an x minus 2 in the bottom, then x could not equal 2. So just be aware of that. That'll come up in our last couple examples today. Here's another definition. Again, this is on that same page, page 416. I think it's just in the paragraph below that green box that the other stuff is in. It's just a quick definition of a power function. Power function is written in the form y equals ax to the b, where a is any real number and b is a rational number. So we know that rational numbers are numbers that can be written as a fraction. So if you see something like y equals x to the 1/2, that's called a power function. Now, you've seen these before. They would just have something like a 2 or a 3 or a 4 in the exponent. Those are still considered power functions because whole numbers are still rational numbers. But these usually, when we write it like this and call it a power function, we're usually referring to something with a fraction in the exponent. So you will start to see functions that have fractions in the exponents. We call those power functions. So the important part today when you see some problems is to figure out what they're actually talking about, and usually you get that from the directions. So now we're saying that we are going to look at this function, f of x equals 2 minus x. So anytime you see f of x, you're going to think of 2 minus x. And g of x in this case is 3x. So anytime you see an f of x, we're going to write 2 minus x. Anytime you see g of x, we're going to put a 3x. And we're going to perform these indicated operations. So first we're going to add the two functions, then we're going to subtract the two functions. Like I said, the tricky part is to figure out what's going on with the domain. It's easy if you look at it from the beginning. So are there any values that we cannot plug in here? Not really, right? You can take 2 and subtract anything from it. That's fine. Is there any number that you're not allowed to multiply by 3? 0. You can multiply 0 by 3. You just get a 0. So right now we have no restrictions on what x values we can plug in here. All right? You'll see some in the future where you're like, oh yeah, we can't make those negative, or oh, if 0 was in there, that would be bad. But right here, these are both fine. So for right now, you can plug any number in for x and you'll be fine. Just keep that in mind when we get to the end of these. We'll talk about the domain. All right, but for now, I want to add the two things. So instead of where the f of x is written, I'm going to write what f of x is. It's 2 minus x. To that function, I'm going to add the g of x, which is just 3x. Next, we'll combine like terms. So negative x plus 3x is 2x. And then you have the plus 2.
That's it.
That's it.
Wow. Can you repeat how you got? I know how you got the 2 minus x plus 3x, but how did you get it to 2x plus 2?
So I just added like terms. So negative 1x plus 3x is 2x.
You just put it in reverse order.
Yep, I put it in standard form. So I always want like the x squares and the x's and the constants. So you start with your x term. Negative 1 plus 3 is just positive 2. And then this is just a positive 2, so plus 2. If the parentheses are confusing you, you can write it without parentheses. So just 2 minus x plus 3, and you're just combining like terms. Now, for the domain, was there any restrictions on either of those functions that we looked at from the beginning? No. So the domain here is all real numbers. Remember, domain is the x value, so you can plug any number in for x, and you'll get an output. You'll get a y.
Is there a symbol for all real numbers?
Yeah, if you want to use the all real number symbol, that's fine. You guys probably know it already. It's that little R with the 2 legs.
Can you show it?
I will. Sorry, my iPad froze up. That guy. That guy. All right, same thing on the next one. That symbol's going to go away as soon as the animation kicks in, so just be aware. Now we're subtracting them. So I still start with f of x, which is 2 minus x, but now I'm going to subtract g of x. Yep, if you want to think of that as plus a negative 3x, that helps some people. We usually distribute that negative when we're subtracting an entire function. So this is negative 4x plus 2. Again, we're looking at those same two functions, and we decided there was no restriction on either of their domains, so there's no restriction on this domain as well. All real numbers. What questions do you guys have? All right, here's 3 and 4. We're looking at the same f of x, the same g of x. So I'm still subtracting them, but now I want to start with g of x. So I'm going to put the 3x first, then subtract the f of x. So anytime you're subtracting something in parentheses, we know we have to distribute it. So I'm just going to change the signs on everything inside my parentheses, and then I'm going to combine like terms. 4x minus 2. We have those same two original functions. We talked about how there was no restriction on their domain, so the domain here, again, is all real numbers.
When will it change?
It will change if you're dividing the two functions. That's when it kind of introduces restrictions. Or if you have something like square root of x as one of your functions, we know that you can't take a square root of a negative number without getting an imaginary solution. So that would restrict our domain to only positive numbers. So things like that you'll have to look out for. I just distributed the negative sign. So I turned it into, instead of positive 2, I turned it into negative 2, and instead of minus x, I turned it into plus x. All right, the next one. This one's kind of interesting because we're taking g of x and we're adding to it g of x. 3x plus 3x is just 6x. Again, no restrictions on our domain for g of x, so no restrictions here either. Here's another way these can be written. So this is just multiplication, so we want to multiply f times g. And instead of giving us the functions and the directions, they're just giving it to us in the problem. So basically I'm taking x to the 1/2 times 3x to the 3rd. Now, x to the 1/2 is the same as what? Yeah, a square root, right? An index of 2 with a radical is just a square root. Eric and I were just sort of talking about this. What numbers can you not take the square root of and get a real solution? Negative numbers. So right now, just looking at the domain of this guy, we cannot plug negative numbers in. We'll get imaginary solutions. So that's going to be considered in our domain. We do not want to include any negative numbers in our domain. Back here, this one's fine. You can plug negatives in, you can plug positives in, you can plug 0 in. This is not the problem, but right here we cannot plug any negative numbers in. So when we get to the domain, remember that. All right, but for right now, I just want to take f. I want to multiply it by g. So you multiply the coefficients first. 1 times 3 gives us 3. What do I do with those exponents? I multiply them?
You add them.
You add them, yes. You can add them in your calculator, you can get common denominators, but either way you should come up with this 7/2. Yep. So 3x to the 7/2. Now, what did we say about our domain? What numbers are not okay here? Negative. So I'm just going to say that x has to be greater than or equal to 0. So as you're writing number 6 in your notebooks, start to think about the domain, because we'll get there eventually. Are there any restrictions on the domain of f of x or the domain of g of x? Because those will come up in our final answer. All right, f of x times g of x. You can write the g of x second. You can write it in the front. Since multiplication is commutative, it does not matter. I'm just going to write it in the front. How do you multiply two things like that? A monomial and a binomial.
2x cubed plus 6x.
Very good. You have to distribute. So we get 2x cubed plus 6x squared. Any restrictions? No. All right, number 7 is our first division example. What did we say you have to look out for when you're dividing? Zeros where? In the bottom. So right now, g of x is forming our denominator here. So what's going to make this guy 0? 0. So keep that in mind when we're looking at our domain. We don't ever want to plug a 0 in because that would make our function undefined. All right, but we can still go through the process. So I'm going to take 4x to the 2/3 over 2x. You can simplify these if you'd like. That becomes a 2. So 2x to the 2/3 over x. Now, some of you might want to simplify the x's. Honestly, if I was doing this, I would probably simplify the x's. But the book likes to leave it this way because that shows our restriction very easily. All right, it shows right away that this cannot be 0. So I would leave it like this just so our restriction is very clear. And we already talked about for our domain here, it's going to be all real numbers except x equals 0. This is our last example of today. Like I said, today is not super difficult, just kind of getting used to the notation. Tomorrow we're going to kick it up a notch when we look at these compositions. As you're writing this, are any restrictions popping out at you?
G equals 0.
Yeah, we can't have a 0 for the g function. G of x cannot be equal to 0, so you cannot use 0 in this one. So just remember that when you're doing your domain. Our f function is negative 7x plus 1, and our g function is x. Can you simplify that? No. You could if you could factor an x out of each term in the top, then simplify by canceling out the x on the bottom. But the way it's written, we cannot simplify it. So you can jump right to your domain. We just talked about how we cannot have a 0 in our denominator, so x cannot equal 0 here. All right, that's all I have for you today. Here is your homework for this evening. You can actually probably get most of it done now. Notice it sort of jumps around, skipping the material that we're going to cover tomorrow. If you get done early and you want to have a look at compositions to be my guest, that assignment is listed on your green sheet. It won't change at all. We are going to pick up right where we left off, so we'll just jump into example 9 when I see you guys tomorrow. Let me know if you have any questions.